So with that, I'd like to open the question, how ancient are parts of the Surya Siddhanta? I only say parts of Surya Siddhanta because Surya Siddhanta has been rewritten several times, several people, but we have evidence there is a core component of Surya Siddhanta that is very ancient. And we can measure that antiquity also. So that's what I like to say over here. How ancient is that? Again, I'm invoking Anil Narayanan's work to do this. It's a fascinating fact again. So Surya Siddhanta has got a model of the sky, right? It's got latitude, longitude of the various nakshatras and so on. But if you compare those numbers to today's numbers, they are greatly in error. And we can wonder why on earth is this error so great? And obviously precision is one of the reasons. So you could have longitude and latitude. So two of them are there, right? So if you take a look at all these nakshatras, Ashwini, from Bharani, Kritika, Rohini, and all these things, Surya Siddhanta has got a brightness. It measures, just like today astronomers measure the magnitude of the relative magnitude of the stars with some number. Surya Siddhanta has got number 3, 5, 3, 2, 1. This is an estimate of Surya Siddhanta on how bright that nakshatra or the star is. And it's got a longitude, Surya Siddhanta longitude, Surya Siddhanta latitude. And the modern longitude, modern latitude. If you look at just the first number, longitude is 8 degrees in Surya Siddhanta. Modern longitude is 34 degrees. Latitude is 10 degrees. The modern one is 8.5 degrees. So clearly, Surya Siddhanta's measurement of the nakshatras was done at an exceedingly ancient period of time, and Anil Narayanan set out to figure out when is the error minimum. He identified which are the quantities that will vary, time obviously, including something called proper motion. Proper motion is, well, the stars are not stagnant in the sky, right? All the stars in our solar system, along with the sun, is going around the galactic center. It takes approximately 230 million years to go once around the galactic center, right? So the movement of the stars as it is going around is called proper motion. Now, all stars are not going at the same speed, like a running race. Some of them are going pretty fast, some of them are going slow, and so on. So from our perspective, some star might be going pretty fast. We can't make out the three-dimensional velocity, but we can make out the angle. From our reference angle, how quickly is the angle where the star is changing. That angle is called proper motion. He also sees the ecliptic obliquity will change, the nodal location will change, vertical motion of the ecliptic will change. So he set about to write a program to do this. And in his program, he found that if he cranks it back in time to 7500 BCE, which is over here, that is when the error became the least. The error between Surya Siddhanta and where our modern numbers are. If he wanted to find a match in time, understanding these quantities are changing, he had to go back in time to 7500 BC to get that error to a minimum. So this is an amazing thing that talks to us about the antiquity of the Surya Siddhanta, for example. In the same Surya Siddhanta, there is a star nakshatra called Swati. Swati is the Greek name is Arcturus. If you want to find out Arcturus, you can first look for Saptarishi. The tail of Saptarishi points to Swati, as you can see over here. So Swati is one of the fastest stars in the sky in proper motion from our perspective, and it has got a motion of 2 arc seconds in a year, like is shown over here. This is a proper motion. This is 2 arc seconds in a year. Now, Swati is off by 1 degree compared to the Greek records. Even the Greeks had observed Swati, Arcturus. If you look at their Greek records and the modern record, and at the rate of 2 arc seconds a year, we can crank back in time and say the Greek observation was made 1800 years ago. However, Swati's latitude position is off by 6 degrees compared with Surya Siddhanta. Surya Siddhanta has got a number that is off by 6 degrees. So if you try to compute that, 6 degrees times 60 minutes times 60 seconds divided by 2 arc seconds, you get 10,800 years old observation. Somehow, Surya Siddhanta, the oldest part of it at least, or maybe it may not be the oldest still, but an old part of it has got observation that goes back to 8000 BCE. So this is staggering to just think about some of these antiquity of some of these measurements. What it is telling us is that Indians as a civilization have expended great amounts of time to observe the stars, to map the stars, to measure the stars, and to pass on that information to posterity. That is what we are seeing in all of these things.